I wanted to build my own robotic arm at one point. And, I thought robotic arms were cool, but I looked around online, they're very expensive. And I thought, how hard can it be? Right, I'll just build on my own. So that was the original idea here. And I did a little bit of thinking early on about what the angles would have to be to keep the gripper level or vertical and stuff like that. And that's all fun and all, but I should really skip to the agenda slide. So my calling thing for the moment for just the arm itself, the bot itself, I call Cujo at the moment. The why was just I wanted to build an arm, and I didn't want to spend $500 or $1,000 or $2,000 for an off-the-shelf arm, and that kind of thing. So I just wanted to kind of share what I've learned in doing this process. I had a lot of fun doing it. I'm not completely done yet or anything, but some of the stuff I learned, in case you guys feel like doing something like this, and like that. So I looked into the theory a little bit of how to position the arm, and how to figure out what angles to put everything at. So each of these sections there is like R1 and R2 are parts of the arm, different sections. And I thought I'd throw a little bit of this trigonometry. I went through it myself, had some fun. A day without trig is like a day without sunshine, right? So a little trigonometry. And and I went through all that theory and stuff and figured out each piece basically pivots around an axis. So you're drawing arcs. Each section follows an arc. So you can figure out the XY position via the trig, and then add on the next piece of the arm, R2 in this case, and then I have the gripper itself, which is another section. And you can kind of calculate, what angles to position the arm sections at to achieve a certain point in XY space, and all that stuff. And I went through all this, and it was a lot of fun, and figuring it all out, and that's great and all. And I eventually said, okay, that's just really hard looking. I'm just going to do it by trial and error, forget the math, So let's do that. Yeah.
Over style.
Yeah, and for now I just want to pick up something at a fixed point in space, so that's not a terrible approach. You can iterate that enough times to get it to pick the thing up. And but if you want to do something that's a little more flexible, where you tell it, go over there and pick something up, over here pick something up, well then you have to have more flexible code that actually does the math. Or you can do Ros and use TF, which will do all that for you. So in a way this is an advertisement for Ros, I guess, but I'm running an Arduino, no Ros on this. So anyway, to get started, I decided to buy these little cheap things from Ros Robotics. They're little things. Normally you put a servo in there and you make a joint, but I think you just flip them around, connect them together, and you can make a section. And they're light, they're aluminum, they're like 4 watts. And you can build an arm with these really light, cheap little aluminum pieces. So I started out with those. And also these Robotic servos from Ros Robotics. I like the way they mount. A lot of flexibility in how you can mount them. They're kind of like the Dynamixel servos, only a lot cheaper. They're like $20 or $25 or something like that. They're PWM servos. They're not digital. They don't have that fancy interface and all that feedback and stuff. But I like the way that you can mount them. They're real flexible. They have more torque than your average high-tech or Frutavo type servo. You can get some very high torque servos from those guys. Anyway, so I settled on those for a while. They have a couple of nifty pieces there for mounting them on other servos or attachment to arms and stuff. And so I have all those pieces too. So the first section of arm looks something like this. So I have those 4 of those little cheap aluminum sections, and then the servo mounts on each end. And that was the beginning of the arm. So I sort of think of it as the base is the shoulder, you have the upper arm, the next servo is the elbow, and then the forearm and the wrist joint. So that's the shoulder and elbow there, yeah. And I just from some of the parts I use, just to kind of share what I found interesting and helpful and worked pretty well. This is also from Ros Robotics. It's their sensor shield. Has lots of pins for plugging in lots of servos and sensors and things like that. It has some flexibility in terms of where you can draw power from, because drawing power from the final supply of the Arduino is a non-starter because the servos draw so much current. So you can use an external supply and tie that into this board. I found it pretty flexible. So I like that a lot. I forget if I have my schematic in here for my other board, but I have a design for a different board that I decided to start on. I'll talk about that in a sec. I'm not sure I have that in here, but we'll see. The other thing is the gripper. And I'm sort of inspired by the whole NASA thing. And one of the samples in NASA is a pink tennis ball, the NASA Sample Retrieval Challenge. And there's other stuff like a hockey puck and a piece of PVC pipe and a bunch of stuff. So you need something to pick up, cylindrical objects and all kinds of stuff. So this is a cheap gripper I found, it's $10, but it's a two-finger gripper. So if you try to pick up something cylindrical with a two-finger gripper, if you're not pretty much on center, it's just going to squirt out, every time you try to pick it up. Right? So I looked online for other grippers, and I found some other stuff that was very expensive, really nice stuff, but it was like 20 grand for a gripper. I'm like, okay, I can't do that. So yeah, no, that's not happening. So I thought of an interesting way to take a couple or three of these $10 grippers and use some hex aluminum standoffs and just mount 2 or 3 of them in parallel. Now I've got a 6-finger gripper, and basically that's what this is. This is my 6-finger gripper. It's 3 of the $10 grippers with some aluminum standoffs that I got from Digicade for 50 cents a piece or something, and 1 servo. So this is about a $60 gripper. It has 6 fingers and pick up all kinds of stuff. So anyway, cheap. And then the other gripper, here's a picture of another view of it, but this other gripper was another thing I wanted to do where originally my 6-finger gripper originally had 3 fingers, 2 on one side and 1 on the other. And it had a little trouble picking up tennis balls, so the gap was too big. That's why it's now a 6-finger gripper. But so in the meantime, I thought what I call this one is a triangular grip. There's 3 fingers coming in, from 3 points around the circle, 120 degrees coming out of the center. And those fingers are from the same $10 gripper kits, but I had to kind of come up with some weirdo hardware to mount and hold and all that stuff. So it's a little difference, but eventually got that working. So that's what this guy is. He's a little heavier than the other gripper, but not by a ton. And it has the triangular grip, which is what I was looking for at the time. Anyway, so ended up with a couple of grippers that didn't set me back 20 grand, which is good. This shows the original completed arm. And the first shoulder servo or base servo was one of the same Ros Robotic servos. And that worked out okay, but it's a little overloaded. I had to do the math, figure out how long the arm is, what actually weighed the arm. So between the length of the arm and the weight of the arm, you can figure what the torque is on the servo. And he was way overloaded. So he did it, but he had a little trouble. So I tried experimenting with higher supply voltages to get more torque out of them. And I emailed the Troston guys and I said, what's the max it can handle? And we're not really sure. And, you can try it. See if you're friable, we'll replace it for you. So I ran it at 9 volts for a while. And sure enough, I tried it. But that's part of the learning experience. And that kind of thing. So anyway, so I decided to get one of these things. And that set me back a little bit of money. My goal was to keep this on the cheap, but I found this really helps for the base servo. It's 7-to-1 gear ratio. I can pick up you can move around a 2-pound camera. So it's nice. You get a lot of torque on that thing. So ever since I put that on, it's been pretty cool. One of the other nice things about that, I don't know if you can see it or not, but he's in what I call the rest position right now. And this would be the position to be in, like retreat, going back to, or going out or going back from, or picking something up. And this mounting plate, when it's all the way down, touches the base, and then the arm lands on it and supports the arm. So I can actually cut power to the arm, not the gripper, of course, because you don't have to drop the ball. But I cut power to the arm to keep the servos from wasting extra energy, and it's well supported. It just kind of worked out that way with this little plate at the top. So that was kind of handy, neat, accidental little feature there. So that's pretty much it, I think, on the presentation. The other thing I wanted to talk about was this other servo interface board I'm working on. So it's probably hard to see, but this board has 6 sets of headers for the 3-pin servos, and then I've wired up 6 0.22 ohm 1 watt resistors in series with the ground connections. And the, I don't have my schematic handy, I don't think, but the top of the resistor, the bottom of the resistor goes to the ground, the top of the resistor goes to the ground connection on the header, and that's also tied to the analog inputs on the Arduino footprint here. So you can actually measure the analog voltage above ground across the resistor and sense the current in the servos. So I'm going to add some code to measure that, and if the current gets too high, back off on the PWM for the servo and to keep it from cooking, that kind of thing. And keep the gripper engaged and without, doing wasting too much current, etc. So, assuming all this works as planned, I'm going to turn on my E switch here. Oh, one second. Got to plug in the battery. It's very important. Why didn't the lights come on?
Awesome.
Yeah. All right, let's try it now. Okay, LEDs came on, very good. So I have this wired up to a push button switch for now. Eventually the idea is another Arduino or can assert drive a pin high or low or can send a command or something, but right now I just have a push button. And assuming I didn't break anything in transit, you'll pick up the tennis ball. We'll see. So far so good. And he's just going out to a point in space. And he's not sensing where the ball is or anything. If the ball's in the wrong place, it's the problem. Yeah. What about us? Good. And that's it? Good. Thanks. Shut it off.
Okay. Needs a racket.
Okay, there were two people over there that said they had robots. Who was the second one? Oh, let's bring her on, huh? Thank you. By the way, getting an arm to work in this club is hard. He's done something that doesn't happen very often. Yeah.
It took a while.
Yeah. That'll be an excellent segue for the main talk.
Hi, I'm Mike, and this is my robot Farron. Begin with the letter F because it's a 6th iteration of this thing. When I'll get done with this, its current purpose is to chase vermin, to detect squirrels. It's going to have, I hope, sufficiently an IR sensor. When it finds anything that lights up as living and makes a move, this thing is going to chase after it, and we will add various increasing levels of weaponry to it to get the squirrels to move out of the way. Meanwhile, it's been as you probably know, everybody in here, nothing about robots is easy, and just everything about this has been hard to get going on this thing. So, and I'm not going to show too much about this tonight because I'm trying to get past networking problems. So, just for those who are interested, this is a LiDAR on top. It's the RP LiDAR. It's a $400 unit. Of course, go out and buy the Neato vacuum, throw the vacuum away, and get apparently the same LiDAR for cheaper. There's a 9 degree of freedom IMU on here, which is accelerometer, rate gyros, and magnetic compass on this thing, which runs through Fusion software to combine it all together to give me orientation. Inside is a RoboClaw motor controller, which is where I've spent a good part of my life trying to make work. Yes?
So on your IMU, whose is it?
It's from Seed Studio.
Okay.
It's just called a 9DOF. From there, they now sell about 6 different versions of this thing. So this thing has an Arduino on it. So you have to download the firmware onto it. It just pipes a stream of ASCII data out there. It's an I2C interface, and it's got an FTDI converter to run USB on it. And as if you people know how magnetic compasses work, there's kind of two types. There's the flux gate compass, which is what the old style was, and it works by saturating magnetic field and then seeing how long it takes the field to collapse based upon the vector of the magnetic field lines going through the coil. That's not this. Those are a lot bigger. It's what I used to use on an earlier invention. I made a 3D bike computer. This is a MEMS device, as I recall, on this thing. But it suffers the same problem. So whenever the robot moves in any orientation at all, particularly roll and pitch, the vector of the magnetic field changes, and so the yaw is way off, and so you have to programmatically correct the yaw based upon the vector of the magnetic thing coming in. And it's influenced by everything nearby it. So there is a calculation routine you can run that will apparently try to cancel out nearby hardcore iron, nearby softcore iron, and all that. But as you drive around, it gets screwed up anyway. So it's a very poor orientation device. The rate gyros help on this thing, and I'm going to put a GPS in here. Of course, GPS won't give you a heading until you move, and on there. And of course, it's well, it's not bad if you're going fast enough and far enough. But odometry is only a hint anyway, in what you're doing on this thing. Like I say, the RoboClaw, man, what problems I've had with this thing. And I've hooked up scopes, I've hooked up USB monitors on this thing, and I've written my own software to drive this thing, which makes it a little better. It works a little longer, but it's constantly timing out the USB bus. It's constantly getting out of sync with the USB device. And even though I go to the resync sequence, it sometimes drops the USB connection altogether, and then the device isn't recognized, and I'm trying to figure out how to force Linux to go through the reconnection with the USB device. But I'm getting through all of that stuff on here. So I'm learning an awful lot of stuff on our group bulletin board. Every now and then I'll post an article about something that I've learned. I posted an article recently about how to get hard naming of your devices, symbolic names of your devices, but it turns out that the only thing you're allowed to do of interest with the UDEV system under Ubuntu operating system is to create a symbolic link. Well, the symbolic thing, the thing that it symbolically links to, is not what you need to run your robot. You can read and write to it, but you can't do control operations, ILCTL, FCTL, those sorts of things. So I had to discover another way to go and look through the Unix device tree and figure out what device was what and work my way back to what is the other device, the character device, that you want to actually connect to on this thing. And I just posted some code that did that last night. So at any rate, this thing is running Ros. It'll run the navigation stack on this thing. But I've been trying to get this to work not on when I'm away from my home network. And so we've got, what is this, Hutu device, which does an access point without you doing anything. You just click the button, turn it on, and boom, there's an access point. You get into your two devices and tell it you want to connect to that access point, and it works like a champ, except that I can now run Ros. I can on here, and I can demonstrate that this thing, will do tele-up, I think on here, sort of thing, and spin around and that sort of thing on here. Thank you. I should probably stop at that. Yeah, I don't want to go beyond what the demo is supposed to be. But I am running Linux in a virtual machine on the Mac. And normally I run RViz there, and I'm displaying, I got a lot of log data, debug data, and all that spitting out. And then I'm running the mapping software over there. And I just changed from running Raspbian on here to a raw basic Ubuntu, because Raspbian was starting to have problems. And now the networking across virtual machines isn't working. So I was going to do what Camp is going to do later on and show you some fancy stuff.
Yeah.
So that's it for me. Thank you, Wayne.
You are not the only person who is suffering the pain with Wi-Fi. Okay, next is Greg, who is going to talk about the SV Ross class and all the fun we had last Monday.
Hello, for those who are new, I run the SV Ros Meetup, where we try to get people to, learn and grow with Ros, instead of being just something you use once and forget, you actually make something out of it. And Monday we had a meeting where I think there were like 15 people there, and I encouraged all of them to show up here with their robots, their Nitos. And so we've got Steve and Camp and Mino brought her robot, so there's 3 here, and it's just, I think, showing the way the club is going to grow, in that now we have a group of people who are using Ros and understanding Ros and actually have working platforms that they can have do something for them. Now, it's a Nito, it's not like it's going to do a lot,
Hey now.
but it's going to fetch you a beer, chase your cat, do all sorts of fun things for a robot, maybe
Navigation.
navigation, open a door for your friends, but it's the start. So now that we've got people kind of past like, oh, I've done Ros, but I don't really know how to make it work, we now have people actually using and making Ros work. So, Camp,
Yes.
you want to show your map of what
Sure,
you
let me
made?
see if I can
And
connect to
Camp
the...
has been working on this project for
years.
3 or 4 years, yes.
So,
And so for him actually having a real map is quite an achievement.
You've probably seen me drive the XV around with the, you've probably seen me drive, I can talk loud. You've probably seen me drive the XV around with laptop connected to the top. The cool thing about this is the Raspberry Pi is in the dirt bin. I shall attempt to, before I plug this in and it all goes south, right now I've got a, actually, Bill,
Can record this.
can you get that?
Oh, Bill's not live.
I'm offline.
It's Osmond.
It's Osmond that needs to focus in on me.
Regardless.
Hold still, hold still, hold still.
You need to hold still so Osmond can
Find you.
steer you.
Where are you?
He's right there.
Camera right
Oh,
there.
okay.
So if you come over by me, oh, now he's coming to you.
We're not going to make this easy, Osmond.
There you go. See, you're over there.
Okay, so here's RViz in navigation mode. I'm running 2D nav. Basically, let me check something here. I'll try not, okay, there. You can see the robot navigating. That's autonomous, no hands. Okay? First thing you do is Ralph Gnock, thank you very much. The G is silent, I pronounce it out of respect. He's built off the Mike Ferguson Nito node. Mike Ferguson's not here? Okay. Regardless. So here I'll click another 2D navigation point, and let's have the robot go back to the corner. So I'll point, press, and drag to set the pose. You see the green line? That's your planning. The robot's actually navigating to the corner autonomously. So the way this works, the Nito has a LiDAR, laser radar, and with Ros, the first thing you do is run G mapping to drive around and create a map. So I've created this map. It's kind of dodgy. It got out of whack, but you can see the whole room here. I drove around and mapped it with G mapping. Then you save that map and you kill G map and you load something called 2D nav. 2D nav allows you to navigate within the map that you've created, which I've done here. So basically you set the pose of the robot, and then you can click on the goal. You point, press, and click the orientation you want to go, and now the robot will navigate to that goal. So, I'm sorry, what?
Can we zoom in?
Zoom in, yes. So for my final, for my final trick, I shall, let's navigate over here. And I need to look, is he doing the whirling dervish there?
Yeah, you got
Okay.
back.
My, okay. My latency's good. Oh, okay, so there he goes. You see the planning. You see the robot navigating to the goal.
Except he's caught in the chair.
You-
Is he? Can somebody move the chair or
He's
something?
kind of out of sync. You want to rotate him to match the map?
Let's try this. I'm going to just, no hands, I'm going to try and pull him out here. Can somebody get the stuff out of his way? Where am I? Oh, I'm all over there. Okay. Tell you what, pick him up and put him in the corner there. Okay? and I shall hit 2D pose and tell him he is in the corner. Boom, now he's in the corner. Okay. Is he still navigating the other way? Let me try to pull him this way.
No, he's not fully in the corner.
Okay, so now he's coming out. Okay. When he gets delocalized, he gets into what's called the whirling dervish. He starts spinning around, so he localizes. But regardless, there you see him navigating to the point. Is there anything in his way?
Nope, just you.
Okay.
He's off by about 90
Thank you for
degrees, though.
that. Okay, so without any further ado, I shall attempt to navigate to, oh shit, that was bad. That's a bug in RViz, I think, because he thinks he's somewhere else now. So I'm going to try to set the pose back to where it was. Okay, and let's try to navigate all the way down to the end of the room.
We've got some other neatos in its way.
Okay, get those neatos out of his way.
So even though he didn't set the pose accurately, it self-corrects?
It's kind of sort of figured it out, and he's traveling as best he can. You know, when you walk along a wall, am I in the chairs now? Let me bring him back quickly to over here. Okay, yeah. Let's move him over there. Oops, he's thinking he's going to go all around the chairs here. We won't let him do that, but I think my time's about up here. I think you get the concept. This is really fun stuff. We are this close to achieving actual A to B navigation, so it's very exciting. Thank you very much.
And anyone's welcome to, participate in the SB Ros, and, you can get caught up pretty quickly. We have an image we put on Raspberry Pi, and if you have a Nito, you can get it running for you. So, thank you.
So I didn't get the mapping done, but I got to do the tally up using the keyboard.
Sweet. You have your mapping, right?
I have my map.
But you don't have, that's a part.
That's not part.
Well, that's a speedy little guy.
We could do like a Nito battle box.
So that's so it just goes around.
Very good.
Now, and once you get to this, navigation is easy. Right. It's just the next step.
Yeah,
It's
that's
really-
my
it's very
next
simple.
step.
It's not that hard. It's actually getting this to work is hard.
Can I coach you on that?
Yeah.
I would just mention that I don't think we've ever had a really successful navigation in the club yet.
Wait a minute, wait a minute.
Wait a
No,
second.
you have not succeeded. I said successful.
Going to the other end.
Max went and picked up the thing outside.
That's outside.
We never had it in here.
You never had one work inside. I just want to be honest,
You want me
folks.
to bring Max and I'll try it inside?
Let's not destroy anything, no. Let's not bring Max in here, okay? I'm just being honest, okay? I expect to see navigation work one of these days. Okay, we're going to take a 5-minute break.